everyone. Today, Głowacki, our PhD student, is going to tell us about the catalog of binary stars from the OGLE project. That's the one of the topics of his PhD thesis. Max is the third year of his PhD studies. He was doing bachelor here at the university in our observatory, working with Igor Stoszyński, who is his advisor of his PhD, and master thesis that was physics, right? And then you came back to the observatory for the PhD. So yeah, the floor is yours.
Thank you very much for the introduction. Okay, I would like to present today the new catalog of binaries in the Magellanic Clouds from the OGLE project. So we'll start with a brief introduction of the OGLE project itself. So OGLE stands for Optical Gravitational Lensing Experiment, and the plan for the experiment was to search for dark matter with microlensing events. The idea was to use the Galactic bulge and Magellanic Clouds for this purpose, as there are a lot of background stars, so we can find a lot of microlensing events while observing those stars. The OGLE started in 1992, and since then it was a large, extensive sky survey. Nowadays, OGLE is already in its fifth phase, and it observed the sky with 1.3-meter Warsaw telescope in Las Campanas Observatory in Chile. OGLE also created OGLE collection of variable stars, which is the largest set of variable stars in the world, and among others, it includes over 75,000 binaries in the Magellanic Clouds that I will focus on in this seminar. What was the purpose of updating the catalog of binary stars? The previous catalog was published in 2016, so we have 8 new years of observation of additional data. So the first point was to update the previous light curves with 8 years of observation, so actually to double the number of the data points. With the new observations, we could refine the orbital periods determined and correct the classification. Also, the previous survey in 2016, the previous catalog in 2016, used a semi-automatic approach. So we had the suspicion that some of the objects might have been missed. So in fact, in this catalog, we found like 50% new objects that are now included. How did we do that? In total, we have 70 million point sources in the LMC and 14 million point sources in the SMC. So for all of them, we have to search for periodic variability. To do that, such an extensive search, we use a very simple software using the FMPix program, which tries to fit a sign function. However, with eclipsing binaries, or in general with eclipsing with binary system, this is not always the best approach, and I will explain why in a sec. So we have to employ other methods as well. And so methods such as string length and fitting higher order Fourier series were employed. And at the last stage, we performed visual inspection of the phase-folded light curves to correct the period manually and to do the final classification of the binary systems. So what are the challenges with finding the period of binary systems? First of all, binary systems have a lot of different types, and there are many different morphologies of the light curves. For example, we may encounter contact binaries which have quite sinusoidal light curve with eclipses of similar depth, which may cause the period that is found automatically to be actually the half of the original orbital period. But we have also much more complex cases. We may have very narrow eclipses and eccentric orbits, which means the eclipses are much closer to each other, not every 0.5 in the phase domain, which simply makes fitting a simple sine function to such system impossible. And during this simple search, such cases would not be found. Also, the most interesting binary systems show other types of variability. Thus, their light curve is not the usual sinusoidal or nearly sinusoidal light curve, so this may also not be found correctly during the standard search, so we have to employ other methods. So in the new catalog, we have stars with magnitudes ranging from 20 to 13, and this is limited by the capabilities of our telescope. We searched for periods from 0.1 to 10,000 days, but realistically, we have objects with orbital periods from 0.1 day to 4,000 days. For the median number of objects found for the LMC and SMC are 879 and 2,274 respectively. It's worth noting that the maximal number of epochs for SMC is around 2,500. So basically for half of the objects, we have more than 2,000 data points. And completeness of our catalog, we estimated about 79%, which is a very good result. So to start the most interesting part of the talk, I would like to talk about the catalog itself. And I would like to compare it to the catalog of binary systems in the galactic bulge. So here on the left, we see the distribution of the orbital periods of eclipsing and ellipsoidal variables from the galactic bulge, and on the right from the Magellanic Clouds from this work. When we first look at it, they look mostly the same. However, at closer inspection, we see some differences. First of all, the peak of the distribution of orbital periods in Magellanic Clouds is shifted towards the longer periods with maximum around 2 days, while in galactic bulge it's 0.4 days. And this is first interesting fact. The second interesting fact is that in both cases we have a second local maximum around 1 to 200 days, and this second maximum actually is not changed. So in both cases it's the same, only the first one is shifted, and we thought what might be the reason for this shift. And we concluded that the most probable reason is actually a selection bias, which means the stars with the shorter periods are usually close contact binary systems of stars that are of lower luminosity. So simply in the Magellanic Clouds, they are not detected because they are too faint. And so the thing is, we simply do not observe this part of the distribution in the Magellanic Clouds. And this can be actually observed by looking at the logarithmic scale. If we compare the ratio of the height of these two peaks, we see that the difference in Magellanic Cloud is around 1 order of magnitude, while in the galactic bulge, we have around 2 orders of magnitude, which actually proves that here we have many more objects than here, so simply we do not observe them in the Magellanic Clouds. Second thing is to compare the distribution of I-band magnitudes, out of eclipse I-band magnitudes for the galactic bulge and Magellanic Clouds. And here again, they look quite similar. However, there are some small differences. In the Magellanic Cloud, the entire distribution is shifted slightly towards the lower brightness to the higher magnitude values. And the second thing we can observe is actually a local maximum around 16 magnitudes. This is most probably due to the presence of luminous stars from the tip of the red giant branch. If we present our objects from the LMC and SMC on the color magnitude diagram, we see that here these stars correspond to the stars of the tip of the red giant branch, and these are these luminous objects that in Magellanic Clouds cause this local maximum on the distribution of magnitudes. Our catalog was actually compared and cross-matched with the other most popular catalogs of binary systems, such as a catalog of Gaia DR3 candidates, VAO6, which is International Index of Variable Stars, EROS-2, and ASAS-SN. So for all of them, we tried to cross-match all the stars with our catalog and compare orbital periods provided by other catalogs with our. And surprisingly, first of all, much smaller number of objects was successfully cross-matched than we originally thought. The worst case was with EROS-2, most likely due to discrepancies in the coordinates. So simply there were so big difference in the coordinates provided in the EROS-2 data set that we were unable to identify the star uniformly. The second problem was that even stars that just by comparing their coordinates should be cross-matched, if we compare the orbital periods in the EROS-2 and some other, especially in Gaia, the orbital periods are quite different. So here we see the most important part of this analysis. So for all the Gaia DR3 sources that were successfully cross-matched with our sources, only 75 of them had the same period. And for EROS-2 data set, only 4.1%, which is surprisingly low result. However, we decided to check for other harmonics of the period, as one of the most common problems that I mentioned earlier was that for light curves that look nearly sinusoidal, or there is small difference between the depths of the eclipses, the period that is found may be actually half of the orbital period. So after including other harmonics, we successfully, let's say, found the matching period for 97.3% of sources. And with Gaia, this was the most problematic because even with including all, not all, but like the 5 nearest harmonics of the orbital period for OGLE, only 75% of sources had matching period. I present this analysis here on those graphs. So each chart corresponds to a separate catalog. We see that we have OGLE period and the period from the catalog. And these red lines symbolize subsequent harmonics. So this main line is the main period, and then we have multiples of the period. And so we see that for ASAS-SN, for example, for nearly all the stars, apart from 3 that are clearly visible here as the black points, the period was successfully matched. And most of it was as the main period, not some harmonics of the period. For EROS-2, what's surprising is, maybe not surprising, this actually confirms our previous idea that for vast majority of the objects we observe that the half of the original period was matched, which is the case that in automatic period searches, we find usually half of the orbital period for binary systems. What was also interesting to observe for EROS-2 dataset that we found points aligning in a specific pattern. So for this one dataset, we observed some period aliases, here labeled with green, orange, and blue lines. For VS6, there was very good match. However, with Gaia, as we can see here, a lot of sources were matched. It is not very clearly visible on this picture because there are a lot of points one on the other. So actually 75% of all the points are along these green lines. However, we see that a lot of objects have orbital periods in Gaia completely different than in OGLE, which basically means that those objects were classified quite by coincidence, because with their orbital period, we don't see any periodic variability, and specifically eclipsing or ellipsoidal variability. Now I would like to present the most interesting objects from our new collection. I will start with transient eclipsing binaries. These are binary systems where the eclipses appear or vanish over a longer period of time. And this is most probably caused by rotation of the orbital plane or oscillation of the orbital plane along the line that we observe the system. As it crosses this line, then we see the eclipses, and as it moves away, we do not see the eclipses anymore. And this is most likely cyclic behavior. However, this process takes such a long time that actually we didn't have the chance to observe the cycle to repeat. However, with longer observations, I hope we will be able to do that. And we have 62 such objects included in our collection. And I would like to share some examples. This is eclipsing variable from the SMC. And here we see on the light curve that actually the amplitude decreases greatly. If we look on the phase folded light curve from this part, or actually not this part, but this part of the light curve, we see clearly the eclipsing behavior. However, if we focus only on the remaining part at the end, we see no more eclipses. However, the ellipsoidal variability remains. Another example could be a star that previously did not show any kind of eclipses. We see some periodic variability, which is most likely the reflection effect. However, recently, after the COVID break in observations, we clearly see the reflection effect with eclipsing behavior. Now, to show that actually the eclipses can vanish and appear cyclically, here we have two examples where initially there was no eclipses, then we have eclipsing behavior, and then these eclipses vanish again. And so, for example, this is the point where the orbital plane crossed our line of sight. And then after some very long time, we would probably be able to see it again. On the upper panel, we see similar behavior. It's not as clearly visible due to the pandemic break. However, it happens much faster than in this case. What is most important that we would not be able to notice such differences during a shorter survey. So basically, we can observe such effects thanks to the fact that OGLE has a 30 years long photometry, which allows to study such changes that happen over larger time scales. Now, the second type of interesting objects are double eclipsing binaries, which are quadruple 2+2 systems. So we have two pairs of eclipsing binaries together, and they show eclipsing behavior with two different periods. We have over 200 systems like that in our collection, and I'd like to show you some of them. So if we phase the light curve with only one of the periods, we see the eclipsing behavior. However, we see that the light curve is somehow distorted. We see like points that are out of the light curve that should be there. And after separating the light curve with two separate periods, we see that actually this panel is sum of these two light curves added together. Of course, these are phase-folded light curves. If you do it in time domain, we will, and then phase it with only one of the periods. This is something that we will see. These are two examples of such systems that we have in our collections. And the next type is binaries with pulsating stars. So these are binary systems when at least one of the objects is a pulsating star. So on the top of the eclipsing behavior, we also see the pulsating behavior. Usually, this pulsating object is a Cephate or type 2 Cephate. Other leader stars are extremely rare, and usually these are other leader type pulsations rather than other leader stars themselves, but I will talk about it later during my presentation. And we have 15 objects in the new catalog, and these are two examples. And this is the light curve phase folded with the orbital period of the system. And then after separating the orbital, the eclipsing part, and then looking for the period for the pulsating part, we are able to separate this light curve into two. So this is a system with a classical Cephate. And here we have another example with type 2 Cephate. We also have binaries with strong apsidal motion, so their lines of apsids experiences precession. This is caused by strong tidal forces or general relativistic effects. And this causes the two eclipses to phase with slightly different periods. We have in total 57 such objects in our collection, and two of them are presented here. So two upper panels show the same object phase folded with slightly different periods provided here and here. As we can see, in one case, one eclipse is phase folded perfectly, but the other not at all. However, if we slightly adjust the period, we can perfectly phase fold the other eclipse, while the first one is completely distorted and we don't see it. And the same here. So this is the example with eclipses with significantly different depths, and here with similar. We also have double periodic variables, so-called DPVs. These are binary systems that show some additional long-term variability. What's interesting about those stars is that the ratio of the longer period to the orbital period is nearly always around 33. So they are somehow related. The origin of the longer period variability is still not known. There are some ideas, however, this is still not a clear thing to the astronomers, and we have more than 200 objects included in the OGLE collection, and I would like to present two of them here. So we have ellipsoidal variable and eclipsing variable. In these two cases, we see that the amplitude of the longer period variability is comparable or greater than the ellipsoidal or eclipsing variability. However, this may vary, so we may have systems with where the eclipsing, the amplitude of the eclipsing variability is much greater than the amplitude of the longer variability type, or systems like that here. And as we can see, the second period is much greater than the original period, and it's more or less 33 times greater than the orbital period. We can also see that on this distribution here, which shows the period ratio of the longer period to the orbital period. We see that it has this distinctive maximum around 33. Of course, there are some objects that are far from the 33. However, They look like DPV stars just by visually inspecting the light curve. However, to confirm that they are actually DPV stars with different period ratio, we need to do some further tests. So these cases are not for now confirmed DPV stars, as we are just inspecting the light curves. However, we see that for majority of them, this is around 33. We have also RS-Canum Venaticorum stars. These are stars where one of the objects is a chromospherically active star, which means that it may develop large spots on the surface, and due to rotation of the star, this spot causes the variability in the luminosity on the top of the eclipsing or ellipsoidal variability. In vast majority of cases, this period of rotation is tidally locked with the orbital period for around 80% of the stars, and we have nearly 300 objects in our collection. Some of them are presented here. We have 4 different objects, and we see that, in fact, we have some, for example, this object is particularly interesting. We see 2 eclipses close to each other, and we see some additional variability, which is due to the star being spotted. And we see that this variability, even if it's phase folded with the orbital period, it still shows some regular behavior, which is somehow synchronized with the rotation of the star. We have also some not classified peculiar binaries, such as this one. This is an interesting example of eccentric ellipsoidal variable, so-called heartbeat. However, it's not a classic heartbeat because it shows additional eclipsing variability. So in heartbeat stars, we have some characteristic pulses. However, in this case, on the top of the pulse, we see 2 eclipses, which are not typically found in such cases. That's why this object is unusual. And we have binaries with significant changes of orbital period. So we see that after phase folding them with even orbital period, we see clearly that there is main signal. However, there are a lot of points not aligning properly, which indicates that probably these objects, they change their orbital period over time. So we try to check that. This is the light curve of the first object of the ellipsoidal variable, and this is orbital period matched for subsequent observational seasons. So we see that in general, the trend is that the period decreases. This period changes around 2.7 times 10 to the power of -5 days per year, which is actually quite significant decrease in orbital period. What's important in this case that even though the period decreases significantly, we do not observe great differences in the shape of the light curve. So basically it's staying the same. This is the light curve from the very beginning. This is the light curve from the part exactly in the middle, and this is the part of the light curve from the end. So we see nothing changed here. However, the second object is much more interesting. We see here similar trend that the period decreases. However, in this case, the rate of period change is around 2 times 10 to the power of -3 days per year, which is very significant change of orbital period. And what's interesting here is that initially we see that this is the eclipsing light curve, and all of the out of eclipse magnitudes are the same in the middle as well. However, at the very end, we see that there is small difference between heights of subsequent out of eclipse magnitudes, which is so-called O'Connell effect. And this may suggest something about possible future of such objects. Why objects with variable orbital period, and why are they interesting? The idea is that maybe they are future mergers. So there was a star FAO 1309 Scorpii, which was a red nova discovered in 208. However, before its discovery as red nova, it was actually observed by the OGLE survey for 7 years before the explosion. What we noticed that this object was significantly changing the orbital period, and the orbital period was decreasing, the same as in our case, with slightly higher rate than in our case, but the difference is not very big. And we see that also the morphology of the light curve changed over time. So similarly, this is the shape in 2004. Then 2 years later, we see similar behaviors in the previous case, that the out of eclipse I-band magnitude changed. So we have this so-called O'Connor effect. And then in 2007, basically the second eclipse completely disappeared. So just before merging, the light curve changed drastically. So it may be worth to observe such systems further, because if we see that the period continues to decrease and the rate of decrease accelerates and the morphology of the light curve changes, it may indicate that it could be a possible merger in the future. So talking about the future, I would like to now talk about further plans of my PhD. The next step after updating the catalog for the Magellanic Clouds would be the new OGLE catalog of binary system in Milky Way. Right now we have over 500,000 new candidates. So this is an enormous number, and there is a huge need for automatization because for such numbers, visual inspection is not very efficient and is very time consuming. And the main difficulty is that we need to find the period very precisely, because once we have the correct period, then we can easily classify such light curves with an automated solution. However, we need to be certain of the period first, and then we need to classify them. And the problem with finding the period is that the objects that are the most interesting are the most difficult to classify, because on the top of traditional eclipsing or ellipsoidal variability, they have some other type of variability, which makes finding the period more difficult than usually. This is one part of the project, and the second part of the project is further analysis of the unusual binary systems that we have discovered so far. So we may, first of all, plan to delve deeper into the origin of the long period variability in the DPV stars. We try to find some relationship between the phase of the long period cycle with the shape of the eclipsing part of the curve, which may hint some shed some light on how it actually works. And the second part is about peculiar pulsators in binary systems and low abundance of Lyrae stars in binary systems that I mentioned before. So some Lyrae stars in binary systems that we know so far are actually not Lyrae stars. However, they are Lyrae type pulsators, which pulsate like a Lyrae star. However, their pulsation is caused by the presence of the second companion. And they are called binary evolution pulsators. So we would like to check such hypotheses for other types of binary systems that are peculiar, that they may be also exhibit similar behavior where pulsations are driven by the presence of the second companion. To sum up, we presented the updated OGLE catalog of eclipsing website binaries. We have more than 50% new objects in comparison to the catalog published in 2016. This is the largest catalog of binary systems in the Magellanic Clouds up to date, contains 75,400 objects, and our collection has objects of particular interest, which are highlighted in the catalog, such as transient eclipsing binaries, double periodic variables, and other peculiar binaries. So there is very important that this data is publicly available and we can analyze them to discover a little bit more about these objects. So thank you for your attention. I'll be happy to answer any questions.
Thank you, Max. Nice work. Any questions, comments? Przemek?
So you mentioned the completeness of the catalog is roughly 8%.
Yes.
Can you first of all tell us how do you define completeness and how would you refine
it? Basically, the fields at which you're observing overlap at some point. So some stars have, some objects have double identification in the OGLE database. So we can observe one object from, let's say, two different fields. And then we see how many of them actually we find in both fields and how many we found only in one field. And then for statistical analysis, we can estimate how many of stars we missed based on that.
So is the completeness a function of magnitude or?
Yes, of course, because if the magnitude, if for stars of lower brightness, the completeness is of course lower because we are limited by the capability of our telescope. So we cannot detect two faint stars.
Okay, I have another question. So you showed us a few examples of objects which show obsidian motion. And you mentioned that this may be the impact of generative events. But the orbital periods here are of the order of a few days. So do you expect GR effects to appear as such long periods?
To be honest, I haven't thought about this. So I'm not a specialist on GR, but that's something to think about.
I would guess it is actually caused by the third body. It's not seen. So you could verify it by checking if the amplitude of the eclipses of this group of objects is near to the distribution of amplitudes of all these objects. And I'm guessing the amplitudes of these objects are generally smaller.
Yeah, I wanted just to specify that the whole collection of variable stars as a whole is not the largest catalog of variable stars, but the largest catalog of manually selected variable stars, because we visually inspect all the light curves. The Gaia DR3 catalog is larger, but they use automatic methods, and most of the parts of the Gaia catalogs are called candidates for variables.
Okay, I have several questions, but okay, I will start with one of those, it was quite interesting for me. You said that you found around 200 quadrupole system, and I wonder how you distinguish if really these four stars are bound to each other, I mean, two binaries, or it is just being close to each other. So from analysis, you can really say that there is a quadrupole system, and you are sure.
So we are, the whole analysis was based just on inspecting the light curves, so we didn't do any additional analysis. With quadrupole systems, the most, let's say, popular and the reasonable cases, actually, there are two double systems, gravitationally bound together. So it's like 2 + 2, because for systems of more than 4 or more stars, the systems when 4 stars are like bound together are proven to be unstable. So the most reasonable assumption is that there are 2 binary systems. Of course, we cannot be sure that they are bound, because there can be very, very close but not bound, and that we cannot actually check. But as far as they appear as one object.
Can you be sure that it is not just something like that you have 2 not bound with each other, 2 binary systems, but being the same direction? Separate.
We can. It is possible.
It's quite possible that some of these objects are as blends of 2 binary systems.
No, I follow up on this, but what is the, can you check what is the expected number of such blends? Because that would tell us that, if you have a model of some distribution, how many times do you expect 2 binaries to get close?
We haven't checked that.
So I think that that's a suggestion, that this is the way to say that these are or not in this part is a not bound system.
I'm wondering what was the most challenging part of your work?
Most challenging part, I would say, probably inspecting the light curves, but yeah.
Still double period variables are, let's say, particular group of stars, or they have different properties?
These DPV stars, yes, these ones. So basically, these are systems when, like, the idea is this is like a separate group of stars. That idea is supported by the fact that this ratio of this longer period is always 33:1 to the shorter period. And there are some theories that this is caused by interactions with the disk and mass transfer between the objects. So there are some, let's say, proposed explanations for that. However, they are not fully confirmed. So that was constitute like a specific group of binary objects.
Say this shorter period is well-defined range, or there are very different.
I don't have it here, but actually there is a whole distribution of possible orbital periods. So I would need to, like, I know the specific graph, but I don't remember the values, but it's not like there are one specific value, because we see that this orbital period can actually span a wide range.
Yes. Colors.
Blue. Stars. This.
I have a question regarding the break in the observations, the COVID break. How much did it affect your results?
Hard to say, probably not much. However, we cannot be sure, because the idea is that something unusual would need to happen, especially in that break, to actually change the result. So we don't see something important. However, like in this case, even if we have this break, the behavior of the star is predictable. Of course, we are not 100% what happened there, but it's very intuitive that it continued along this pattern. So unless for some specific object something extremely interesting happened, especially in that break, and we missed that, then I would say it's not that impactful. For example, for this quadruple system, sometimes it's that one can even cover the other, and that happens very rarely, or with a third companion that they can cover the binary system. It happens quite rarely, so that we would miss, but it's very rare, so we don't know if we missed it.
Any more questions, comments, anything on Zoom?
No question.
Okay, so let's thank Max again. Thank you. Next week, Michał Pawlak from Lund Observatory, our alumni, will tell us about search for dormant black holes. See you. Thank you. Very nice.
Załamałem głowę.
Bardzo ładnie.